The greatest of human endeavors is a risky business, and even in the elite world of space exploration, problems arise. While NASA has led humanity into the cosmos, behind the scenes, out of the public eye, mistakes, mishaps, and failures have plagued the space industry. But what happens when the very human element meant to drive discovery also leads to disaster? From a simple twist of a joystick that scraps a critical space shuttle component to a catastrophic $100 million probe spiraling out of control, we uncover how NASA's most astonishing failures have ultimately propelled us further into the cosmos, revealing secrets about our universe and ourselves. NASA's often forgotten predecessor, the National Advisory Committee for Aeronautics, or NACA, was established in 1915 to compete with German aircraft design during World War I. NACA propelled American aeronautics from those early, fragile wooden and fabric biplanes of yesteryear to the world's very first supersonic flight. This historic achievement was made by the rocket engine-powered X-1, piloted by future astronaut Charles "Chuck" Yeager in 1947. 11 years later, on October 1, 1958, in response to the Soviet Union's successful launch of Sputnik, NASA was born. Since then, NASA has brought us the Mercury program, Gemini and the first American spacewalk, Apollo and the moon landings, 3 decades of the Space Shuttle program, and the International Space Station, tomorrow, Mars, and beyond. NASA's success with each groundbreaking achievement, from the distant past to the far future, depends on the knowledge gained and the technology developed from past programs. While technology is fundamental to space travel, the most vital factor in NASA's successful journey into the great beyond is its people. Their creativity, courage, motivation, and their bold, endless drive to go where no one has gone before. However, being human also means making mistakes. Decades of research have shown that most space failures are caused by human error. First, NASA was forced to scrap a critical and expensive piece of space shuttle hardware when a technician made a wrong turn. NASA's highly sophisticated Coordinate Measuring Machine, or CMM probe, measures machined parts on any axis, down to less than 1 micrometer. This CMM probe is used, among other things, to measure components of the Space Shuttle orbiter's cold plates. A cold plate draws heat from the Line Replaceable Unit (LRU), avionics, and radios within the shuttle. Inside the Space Shuttle orbiter, LRUs, including avionics boxes, control numerous critical functions. These LRUs produce significant heat, which cannot be traditionally vented or cooled due to the sealed environment inside the crew module. Cold plates are installed against the LRUs, and heat is drawn off through convection, keeping them cool. Failure to cool the LRUs properly could be fatal to the crew. The cold plate's core material is machined into a single component that includes more than 30,000 individual protruding pins. These pins are designed to meticulously control the flow of coolant through the cold plates. They must be incredibly precise because during testing, fluid is flowed through them at a specific rate to ensure sufficient heat extraction. Machining those 30,000 pins in is a precise, time-intensive, and expensive process, taking weeks to complete a single cold plate. It requires approximately 80 manufacturing hours, spanning 2 shifts over 2 weeks, because each tiny pin is machined individually. Afterward, every one of those 30,000 pins must be checked with the CMM probe to ensure it meets precise dimensional requirements. These detailed measurements ensure everything matches the print specifications. Operating the probe is generally straightforward, but in a bizarre accident, many hours into the process of checking every pin, everything unexpectedly went wrong. The operator was measuring a part and needed to move to the next area. This required the machine to move upwards and over. But instead of moving up, the probe suddenly went down, damaging the cold plate and the CMM probe itself. It caused a hole, a dent, and damage to the equipment. Technicians were stunned and confused. A cold plate had never been damaged in the CMM probe shop. Was it a technology failure or operator error? NASA's investigation would reveal why a 15-year veteran operator's perfect record suddenly came to an end. A highly sophisticated CMM probe in the hands of a meticulous, experienced operator, and the unthinkable happens. Space Shuttle cold plate operator Fred Vivier immediately called his supervisor to report the incident, but his supervisor didn't believe him at first. It took Fred a while to convince him that it had actually happened. Some inspectors were known to be practical jokers, so when Fred called, the supervisor initially dismissed it. It took about 20 minutes on the phone to convince him, given the immense man hours and machine hours invested in making that part. A really bad, sick feeling came over him due to the nature, time, and criticality of the part. Fortunately, damage to the CMM probe was limited to the ruby tip on its stylus, which was quickly replaced. The cold plate, however, was a different story. The probe ended up impacting a very thin wall on the cold plate, causing a dent and a small hole. The cold plate core was scrapped. It no longer met NASA's strenuous safety requirements. This was detrimental to the program at a time when they were trying to meet a schedule, setting them back considerably. They simply had to build another core. Building another core would take at least 80 man-hours, a costly operation. Manufacturing a new cold plate and repairing the ruby-tipped stylus solved the hardware issue, but it didn't answer NASA's most pressing questions. How did it happen, and why? These questions had to be answered before any other cold plates could be inspected, as NASA could not risk damaging another mission-critical piece of hardware. NASA needed answers, and fast. The CMM probe involved in the accident was new, having replaced an older machine that had broken down. The machine's software and mechanical functions were working perfectly, but like so many other space mistakes throughout the years, the accident was the result of a simple human frailty: operator error. A skilled operator with a flawless 15-year record made a wrong turn, costing the space program tens of thousands of dollars and weeks in delays. He mistakenly twisted the controller the wrong way, and it went down instead of up. But this wasn't a simple case of lack of attention to detail. The operator was one of the best in the business. Why did he make such a costly error? There was no rush, and knowing Fred, he was concentrating on what he was doing. The supervisor believed it was the way the machine was set up. Had it been oriented correctly, it would never have happened. The old machine had different controls, with the probe controlled by 2 joysticks. The new CMM probe, however, was controlled by a single multifunctional joystick. This one joystick could make it go up, down, right, left, forward, and backward. If twisted clockwise, it would go up, but if twisted counterclockwise, it would go down. The cold plate was destroyed when the controller was turned the wrong way. While this might not be a big deal for a home improvement project, this was NASA, and this was unacceptable. The measurement of cold plates had to be foolproof. Investigators were closing in on both the root cause of the accident and a solution that would guarantee future success. When the new CMM probe was purchased, each technician spent hours training on it. Once the machine arrived, all 4 inspectors underwent a week of specialized training with the company representative as part of the purchase contract. But the root cause came down to a human trait known as automaticity, a pattern or habit resulting from learning, repetition, and practice. Walking, driving a car, or always putting on your right shoe first are examples of automaticity. These ingrained habits are formed from years of repetition, even, according to some studies, altering our brain patterns, making relearning or unlearning certain habits extremely difficult. The new controller required the joystick to be turned clockwise to go up. However, the technicians were trained by years of experience that, according to American standards like righty-tighty, lefty-loosey, turning right meant going down, and turning left meant going up. 1 week of intensive training on the new machine was not enough to counter years and years of subconscious habit. Putting more space shuttle hardware at risk while technicians developed new habits was unacceptable. Through extensive coordination with the manufacturer of the new CMM probe and software engineers, the programming was altered to make the probe go up when turned counterclockwise and down when turned clockwise. This modification ensured the probe was far more intuitive for the operators. Additionally, one more failsafe was put in place. Directional labels were added to the controller. Since then, there hasn't been a single problem. The operators look at the labels, take the time they need, and there haven't been any other issues at all. Next, a spectacular crash incites an equally spectacular recovery effort to salvage a $100 million mission and billions of years of science. On August 8, 2001, NASA launched a Delta II rocket from Kennedy Space Center carrying an unmanned vehicle on a little heralded search for the origins of the universe. It was a quiet launch, save for the roar of the Delta II's engines. There were no spectators on the beach, no space fans atop campers, no massive crowds cheering as the Delta soared away from its launch pad. You might think there would be, because this unique scientific mission was, in many ways, traveling back in time, billions of years, to the very birth of our solar system. After years of preparation, the world's scientific community was filled with anticipation for what the spacecraft might bring back. The unmanned spaceship was named Genesis, because it headed into space seeking answers about the beginning. Genesis was destined for an orbit within an orbit, 6 million kilometers from Earth, in direct line with the Sun, to catch solar rays and return them to Earth. The spacecraft was armed with a variety of unique collector arrays designed by NASA to capture the purest solar wind ions possible from the outer layer of the Sun. Scientific evidence suggests this outer layer hasn't changed since our solar system was born from its original nebula some 4-5 billion years ago. Ions in the solar wind have been called the fossils of that nebula, meaning theoretically they should tell us if our solar system is made up of the same material that formed that original collection of ice, dust, and gas. If so, NASA believes those solar winds could also hold clues to the origins of life itself. The Genesis mission marked the first time space matter had been returned to Earth in 3 decades, since astronauts brought back samples from the Moon. On November 16, 2001, Genesis slipped into an elliptical orbit around Lagrange point L1. Lagrange points are gravity-balanced zones between celestial bodies, and L1 sits directly between the Sun and Earth. As Genesis orbited L1, L1 in turn orbited the Sun. L1 was selected as the focal point for this critical mission, partly because, at 16 million kilometers away, it is devoid of Earth's atmosphere and contamination. After establishing its orbit within an orbit, Genesis deployed its solar panels to draw energy from the Sun. Then, the primary collectors opened and were exposed to the solar wind. The ions from the solar winds began crashing into the collector arrays, traveling at speeds exceeding 40,000 kilometers per hour. On impact, the ions were buried into the surface of the collectors. These hexagon-shaped wafers consisted of a variety of super-pure materials including silicon, commercial sapphire, gold, and diamond-like carbon film, some expected to capture the elusive solar wind better than others. Secondary arrays were automatically deployed when Genesis encountered special solar wind events like coronal mass ejections. The purity of the ions was critical. NASA wanted pristine fossils of the solar system's birth to ensure maximum scientific value. Throughout the years of planning and manufacturing, the collector arrays were handled with extreme care in clean room environments, with a focus on maintaining the critical purity required. These samples would be available for the scientific community for decades to come. For 850 Earth days, the solar wind blasted Genesis. Then, on April 1, 2004, after completing 5 halo loops around the Sun, the collector arrays were retracted and stored in the Sample Return Capsule, or SRC. Genesis then began its 6 million kilometer journey back to Earth. Having spent 2.5 years collecting solar wind ions, the final phase of the mission would be the SRC's entry, descent, and landing. NASA was taking no chances. An elaborate EDL plan was devised to ensure the capsule returned as gently and safely as possible to protect its ancient cargo. Traveling at over 40,000 kilometers per hour, Genesis would smash into Earth's atmosphere and immediately begin slowing due to atmospheric resistance. This rapid deceleration was designed to trigger a series of mechanical events that would deploy a drogue parachute, stabilizing the SRC and slowing the spacecraft's descent. The SRC would continue to slow until it reached an altitude of 6-7 kilometers. At this point, the drogue chute would be released, and a large parafoil deployed to further slow the descent and ensure the return capsule maintained stable flight. To further safeguard the precious cargo, a helicopter with a 5-meter-long hook would capture Genesis by its parachute and gently lower the spacecraft to the ground. NASA selected the United States Army's Dugway Proving Grounds as the landing site. Located about 137 kilometers southwest of Salt Lake City, Utah, it is a vast desert wasteland. Founded in 1942 and notorious for top-secret chemical and biological warfare testing, including the rumored release of the nerve agent VX in 1968, killing over 6,000 sheep 30 meters away from its test site, and the production and mishandling of live anthrax as recently as May 2015, Dugway is highly guarded and its airspace restricted. It provided a vast isolated area for the landing of the Genesis capsule. Weeks in advance of Genesis's return, NASA rehearsed the mid-air capture multiple times. Scientists around the world had been waiting for 3 long years for Genesis's return. NASA was ready, confident in their recovery plan. The Genesis sample return capsule entered the atmosphere right on time on September 8, 2004. But then, everything went wrong. The capsule began spinning wildly out of control, plummeting to Earth at hundreds of kilometers per hour, leaving NASA scrambling to save the mission. Stunned, NASA watched helplessly as the capsule, filled with the mysteries of our solar system, plunged to Earth. Recovery teams reported, "Mark, your range is 16 kilometers now, sir. It's coming down through 61,000 meters." 16 kilometers, 61,000 meters. Thank you, Major. MCC, we are able to identify a tumbling object in Mission Manager MTC, be advised. From our vantage point, we do not see a drogue negative probe. NASA pulled back the recovery team, including the mid-air capture helicopters, because the parachute deployment sequence was a fail-safe mechanical system triggered by re-entry. There was nothing NASA could do to activate the parachutes manually. "It looks like we have a no-shoot, sir. Vector 2000, put it on your nose. 13 kilometers, look for an impact." Then came the chilling call, impact. Impact at 58:55. When the prized capsule slammed into the Utah desert floor, a seismic emotional shockwave struck research labs around the world. Like a forged aluminum Icarus, NASA's flight to the sun had ended in tragedy. The SRC lay in pieces, the sample capsule breached, and the most carefully protected unmanned payload in NASA's entire history lay in a sunken crater of dugway dirt that had been exposed to 60 years of chemical and biological weapons testing. The recovery team was not allowed near the capsule due to toxic gases from the SRC's batteries and the unfired drogue chute explosives. As they waited for access, questions filled the air. What went wrong? How bad was it? And what about the solar wind ions buried deep in the pure element collectors? After the gases dissipated and the explosive charges were disarmed, the NASA recovery team went to work to recover even the tiniest fragments of the collector arrays. The arrays and solar collectors, in 15,000 pieces, were carried with buckets of debris and desert sand to an impromptu clean room. Scientists began the painstaking process of separating the shattered arrays from sand and other wreckage, with the ultimate goal of determining if contamination had destroyed all scientific value in these priceless pieces of the ancient past. Meanwhile, NASA investigators wanted answers. How could a $100 million mission end in a devastating crash landing? The investigators focused their attention on the failure of the drogue chute. NASA had used parachute re-entry systems in one form or another since the very beginning of the space program. It was regarded as a heritage system and was expected to always work, well, almost always. When the capsule left the vacuum of space and hit the density of Earth's atmosphere, a switch called a gravity switch, or G-switch, was designed to be thrown forward, sending an electronic signal to 4 explosive charges that would blast away a cover plate to deploy the drogue chute. Just like when driving a car and hitting the brakes, anything not secured will be thrown forward. The gravity switch works on the same principle. The force of the atmosphere meeting the momentum of the spacecraft throws the switch forward. This switch starts the automated landing sequence. There are very few ways it can fail because it is not computer or electronically activated. It is a rocker switch that simply rocks forward when the spacecraft hits the atmosphere. Genesis was equipped with 4 gravity switches, 2 primary and 2 backup switches, installed in case the 2 primary switches failed. Investigators recovered both the primary and backup gravity switches from the wreckage and found them perfectly intact and, crucially, not activated. While scientists worked tirelessly to salvage the solar wind ions, NASA was about to discover the shocking cause of the crash. With the Genesis capsule wrecked, and scientists desperately trying to determine what, if any, scientific material would survive, crash investigators reviewed the spacecraft's design plans and engineering paperwork. Everything appeared in order. The paperwork indicated the gravity switches were installed properly, along with the drogue chute and parafoil. While frustration with the investigation mounted, a small ray of hope began to emerge from the science recovery team. Some of the collectors were still intact, and the pure element wafers appeared to have done their job. Many of the long-sought ancient ions remained pristine and uncontaminated. One of the collectors was a piece of gold foil, described as being like very, very thin aluminum foil, but made of gold, and thus even more fragile. Yet it was completely intact, not damaged at all. While the scientists were feeling optimistic, the crash investigators were not. Then, an X-ray examination of the switches finally provided a breakthrough. The primary switches were backward, and the backups, they were backward too. As the sample return capsule entered the atmosphere at over 43,450 kilometers per hour, the dense atmosphere began resisting the spacecraft, which should have thrown the switch forward. But because it was installed backward, the switch did not move. It could not be thrown into a forward position because it had been installed in the forward position. The drogue chute never deployed, causing the capsule to tumble out of control. So, when the spacecraft hit the brakes, the switch was already forward and didn't move. Once again, human error had proven disastrous. A wide-ranging investigation revealed that engineers from another program had made design changes to the avionics unit, which shifted the circuit boards and the gravity switches installed on them. A standard centrifuge test would have caught the problem, but the test was not performed because the Genesis avionics unit was delivered 4 months late for testing. Furthermore, the gravity switch was considered a heritage system that was approved without the test. But NASA concluded that the design changes should have required the additional testing, learned from the mistake, and implemented rigorous reviews and evaluations of all mission-critical systems for every mission, issuing a notice that just because a system has a backup, it still must be checked as reliably as all other systems. The spectacular crash landing of the $100 million Genesis sample return capsule starkly demonstrates the risks of human error to space exploration. But human ingenuity, resilience, and a lot of hard work ultimately salvaged the science. NASA declared that all the mission's primary objectives were achieved, and groundbreaking research continues to be conducted on the recovered solar wind ions. Studies on oxygen and nitrogen isotopes, as well as neon and argon isotopes, have confirmed some solar theories and revealed surprising levels of oxygen in the sun. Research continues, as even if something cannot be analyzed today, with advancements it may be possible in 5 years. As humans continue to reach for the stars, driven by the spirit of exploration and the joy of discovery, human error is always a possibility. But human determination will always find a way to fix the problem, to go further, and to discover more.